So do you want to go through the entire thing like last time, or you have specific questions? Yeah. Whole thing? Okay. All right, so let's start with the first one. So as I said, there will be two questions on the exam. One will be on eigenvalues, eigenvectors, diagonalizable issues, right? And the other one will be on T-invariant subspaces, T-cyclic subspace generated by something, and the Cayley-Hamilton theorem. I would expect more weight to be given to the first one, the one with diagonalizability. Let's start with the first one. Part A. You have a vector space spanned by 4 vectors, which are functions. It is a space of functions, f1 through f4, given here, x sine x, x cosine x, sine x, and cosine x. Maybe I should write them down instead of going back and forth. So V is the span of f1, f2, f3, and f4 in this order. And the operator is d from v to v. D is defined by d to dx, so derivative with respect to x. So part A, you need to find the matrix of this operator in the basis beta, where beta is this basis here. Okay, so to do that, it's going to be a 4 by 4 matrix, so you have to start applying d to each of the 4 functions. So d of f1, that's the derivative of f1, so product rule is sine x plus x cosine x. So what's the first column? 0, 1, 1, 0. Right? F2, derivative is cosine x minus x sine x. So negative 1, 0, 0, 1. Derivative of f3 is cosine x, so 0, 0, 0, 1. And derivative of f4 is negative sine x. 0, 0, negative 1, 0. Okay, so we're done with part A. Part B. Find the eigenvalues of A when the field is the set of real numbers. So we need to find A being this matrix that we found in part A. So we need to look at the determinant of A minus T identity 4 by 4, which is the determinant of the following matrix: negative T, negative 1, 0, 0, 1, negative T, 0, 0, 1, 0, negative T, negative 1, 0, 1, 1, negative T. Now, how do you find the determinant of this matrix? Cofactor probably along the first or the second row. Let's do the first one. Negative T times the determinant of this matrix, right? So negative t times negative t cubed plus 0 minus t. Negative t cubed minus t. And then plus negative 1, but it's times negative 1 to the power 1 plus 2, because it's row 1, column 2, so another negative 1. So it turns into plus 1 times the determinant of which matrix? 1, 0, 0, 1, negative t, negative 1, 0, 1, negative t. What do you get? T squared, 0, 0, 0, plus 1, t squared plus 1. I hope you're following, I don't know. Because if I'm messing up the computations here, everything will be destroyed, right? So, t to the fourth plus 2t squared, but no, I think that's it. I remember this kind of thing, and it looks too nice to not be the right answer, because it factors like this. All right, so the characteristic polynomial is t squared plus 1, everything squared. It said, find the eigenvalues of A when f is R. So the answer is none, right? A has no eigenvalues. When f is R. Part C, find the eigenvalues of A when f is C. Now, when f is C is a different story here, right? Because this polynomial has complex solutions, and they are I and negative I, each of them with multiplicity 2. Okay. So, okay, part D. Is the matrix A diagonalizable when f is R? Why not? It has no eigenvalues. Well, actually, that theorem for diagonalizability was requesting two things. It doesn't specify no eigenvalues, but it says the polynomial, the characteristic polynomial, should split, and the dimension of every eigenspace should equal the multiplicity of each eigenvalue, right? So the reason, the actual reason for it not being diagonalizable is that the characteristic polynomial doesn't split over R, which is actually equivalent to not having real eigenvalues, but you know, if you were to cite the right theorem, that would be it. So A is not okay, since the characteristic polynomial does not split over R. Second part of question D, is A diagonalizable when f is C? Okay, so that would be part 1. Part 2. All right, so now that's a different story, right? Because over C we have 4 eigenvalues, actually 2 of multiplicity 2 each. So we can, continue those arguments and actually look into the eigenspace for each of those eigenvalues and see if it is diagonalizable or not, right? So we go further here and we look at E lambda 1 and E lambda 2, so the eigenspaces. So E lambda 1 is the null space of A minus lambda 1 identity, so A minus I identity 4 by 4. And that is the matrix. So this one here minus I. Okay, so negative I, negative 1, 0, 0. So I have it here. Thanks. 1, 0. 0, 1. All right, so this is what the matrix becomes, and I want to find a null space, which means if this is multiplied by x1, x2, x3, x4, that should give me 0, 0, 0, 0. Negative I x1 minus x2 is 0. x1 minus I x2 is 0, which are one and the same. Because if you multiply the first one by I, you get exactly the second one. Right? I squared is negative 1. Okay, then x1 minus I x3 minus x4 is 0. And x2 plus x3 minus xi x4 is 0. Which I suspect they are the same again. So x1 is I x2 from the second or first equation, because it's one and the same. And if you replace it in here, and imagine multiplying everything by I. If you multiply everything by I, you should get the same thing, do you?
Does the negative I, is that a plus I3 or a minus?
This is a plus. If you multiply by I, it gives you negative x2 plus x3 minus I x4 equals 0. That's not good. Because that means x2, well, I don't know. So do you see any mistakes so far in what I've done? Computational mistake I made. Well, okay. So if you multiply that one by I, you get negative x2 plus x3 minus I x4. And the last equation says that x2 plus x3 minus I x4 is 0, right? If you subtract the second from the first or backwards, x2 is 0, right? Because x3 and I x4 will just go away. x2 is 0, but if x2 is 0, x1 is 0, according to this. And x3 and x4 are then related through this. From the last equation, right? And from the one above, it should be the same thing, and it is the same thing. So what does that mean for the first eigenspace? What would be a basis? Well, let's look at the solution. The solution looks like this: x1, x2, I, x4, x4, right? So E lambda 1 is just the span of this vector. Is that good?
Does the one have multiplicity?
It had multiplicity too. That's why I didn't like what happened back there.
So
But
shouldn't there be?
well, it should if the matrix would be diagonalizable, but that means it's not diagonalizable, right? Because the dimension of this eigenspace does not equal the multiplicity of the corresponding eigenvalue. Probably I made some mistake because I wanted it to be diagonalizable over C, and then to continue with the third part of this question. So at this point I'm done, right? I stop because so the answer is no, it's not diagonalizable. And the third part was if A is diagonalizable, find matrices Q and D such that A is Q, DQ inverse, right? At this point that's nonsense, right? It doesn't make sense anymore because it's not diagonalizable, so. But anyways, I would expect to be more careful on the exam, and that will happen. So how do you find those matrices Q and D? So D is, you just list the eigenvalues in whatever order you want, right? And for the matrix Q, you place the columns. In the columns, you put the eigenvectors corresponding to the eigenvalues in that order that you chose for D. Yeah.
We never did an example where the E lambda was more than 1. All of them had only one vector in them. What would it look like, the equation over there, if they had two vectors instead?
Let's look at E lambda 2, because I have a feeling that will be like that. So again, that's not part of the solution. We don't need that anymore, but let's just look at E lambda 2. That's the null space of A minus lambda 2, so A plus I identity. And the matrix will be the same, but with plus on the diagonal. So I, negative 1, 0, 0. I hope I'm not wrong, because everything is so symmetric here that I'm starting to have doubts. 1, I, 0, 0. No. 1, 0, I, negative 1. 0, 1, 1, I. Well, the purpose of this review section was to create solutions, so. All right, let's see what happens here. I, x1 minus x2 is 0. x1 plus I, x2 is 0. Are they one and the same? Yes, because if you multiply the second one by I, you just get the first one. So all we get out of that is that x2 is I, x1. Let's move to the third. x2. Yeah. And the answer is still no. Because if you replace x2 by ix1, right? If you multiply everything by I, you get negative x1 plus I x3 minus x4 equals 0. So of course the same thing happens as in the one above. X1 will be equal to x2 will be equal to 0, and x3 will be x4 will be ix3. Okay, so that doesn't answer your question. So going back to your question, how can it happen that you have two vectors or more in E lambda? Well, E lambda comes from solving a system of linear equations, right? And you know that a system which is 4 by 4 here could turn out to have up to 3 free variables, right? In this example here, and in the one above. So let me look at the one above, because I wrote more about it, so I wrote everything about it. So here x1 and x2 were 0, and x4 was the only free variable, right? The one that could be anything. So it turned out that the dimension of E lambda 1 was 1. And this null space will always have the dimension equal to the number of free variables. Okay, so let's say that you solve some system of linear equations, and you end up with x1 equals 2x2 plus x3, and x4 equals 3x2, 3x2. Okay, x2 and x3 are free. Right, so let's say that this will be the some E lambda from the null space of that thing would result this. What would be the solution set then? Well, it will look like this. x1 is 2x2 plus x3. x2 is free, x3 is free, and x4 is 3x2. You place everything in the solution, but then you have to break it into two vectors, right? So one is the one containing x2, so it's x2 times 2, 1, 0, 3, plus x3 times 1, 0, 1, 0. Okay, so in this way you get the span of two vectors. So for short, your answer is the number of free variables of the system will give you the dimension of the eigenspace. So that's the end of question 1. Let's look at 2. T-invariant subspaces, T-cyclic subspaces, and something related to Cayley-Hamilton. I will try to have them connected to each other when creating the sample problems. That wasn't the case, so there are 3 completely disconnected questions here, but anyways. I'm missing an N. All right, so we have a linear operator defined by that. T of f of t is that integral times t. And we have a subspace. You're told that it is a subspace. You don't have to check that. You only need to check whether it is T invariant or not. So what do you do? when you want to check that something is t invariant, what do? You just apply t to anything, something arbitrarily, chosen in W and see what happens. So I'm going to take an element like this, AT plus B, and apply the operator to that. Just make another page because it's simpler to move between pages. Okay. So you apply t to a function like this. So that's the integral from 0 to 1 f of x dx. So f of x is ax plus b dx, everything times t. And that's ax squared over 2 plus bx, evaluated from 0 to 1, everything times t. And when you plug in 0, you get 0. When you plug in 1, you get a over 2 plus b. Everything times t. So now, is this result of the form of an element in W? So an element of W is a linear equation, right? A linear function of t. And we got something times t. It is linear, right? So it is in W. If you look over the notes, I just picked one that was different from the notes and the homework, but there are, other examples in the notes like the range, the null space, eigenspaces, and in the suggested homework. By the way, the last homework turned into suggested lately, because the solutions will show up on Friday anyway, so it will not be collected. So there are plenty of examples in all those things about T-invariant subspaces.
I didn't know if it was in W because it looks like W was just something that was like AT plus B and AT plus BP.
Well, this is, can you see it as C times T plus 0? A and B could be anything, right? In the definition of W here, for some
A
and B, they could be anything. So B is 0, A is that thing. Okay. All right, part B. You have a linear operator on the space of 2 by 2 matrices defined by this. T of a matrix A is the product between this fixed matrix 1, 1, 2, 2 and whatever matrix A you choose. Find an order basis for the T-cyclic subspace generated by Z, where Z is that matrix 0, 1, 1, 0. So first, what is the T-cyclic subspace generated by Z? Is the span. And then you throw in here Z and T of Z and T of T of Z and T of T of T of Z and so on, right? Dot, dot, dot. All those things are in there. Let me write the function again. T of A is 1, 1, 2, 2A. See? And Z is the matrix 0, 1, 1, 0. Okay, that's the first element, so we need to find T of Z first. Now, do you remember how it worked when you're trying to find the basis for the T-cyclic subspace? There was a result from last time that was saying that if the T-cyclic subspace has dimension k, all you have to do is to go up to T to the power k minus 1, right? From the vector up to there without skipping anything. Now, of course, you don't know what the dimension of this space is, right? It's part of a matrix is 2 by 2, so it's at most 4, right? But in order to find it, you keep adding vectors to Z until you get to a set that is no longer linearly independent, because that was our proof. That's how we proved that result. We found the maximal linearly independent set, and that turned out to be a basis, right? So we'll kind of follow the idea from the proof. So we apply T of Z, which means multiplying those two matrices. So we get 1, 1, 2, 2. Of course, this is Z by itself. So now I'm trying to add this to the set as long as it is linearly independent, and it definitely is, right? There is no way to get a linear combination of those two equal to 0. All right, so let's see if we can add another one. The next one will be T squared of Z, which is T of the result, right? That one here, T of Z. All right, so T is multiplying by this matrix 1, 1 to 2, so I just need to multiply it to itself. All right, so I get 3366. If I place it in, it becomes dependent, right? Because it's 3 times the previous matrix, so I cannot place it in. That means I close the bracket here and I'm done. The T-cyclic subspace has dimension 2, and that is the basis. Okay. And part C will be about the Cayley-Hamilton theorem. So A is an n by n matrix. Show that the dimension of the span of the set containing the identity A squared, A cubed, dot, 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 an infinite set, cannot exceed n. All right, so what is the connection between this and Cayley-Hamilton? Now let's try to remember what Cayley-Hamilton was saying. It was saying that an operator T satisfies its characteristic equation or characteristic polynomial. If you replace little t by big T, the equation is satisfied. The same holds for matrices, right? So Cayley-Hamilton says that if f of t is the characteristic polynomial of A, then if you replace t by A everywhere, you're going to get the zero matrix. Okay, now of course I don't know what the characteristic polynomial of A is, but I know a couple of things about it, like I know its degree, right? The degree of the characteristic polynomial is n, always n. So f of t, and I also know the leading coefficient. Is not important, but anyways, let's put it here. Negative 1 to the n, t to the n, and then the rest of the terms. So if this is a characteristic polynomial, then Cayley-Hamilton says that when you replace t by a, which gives you this, you get 0. No matrix. Okay. And now, how can we use this in connection to that set?
That's what it is.
It is in the span of that set, correct, but the idea is, in order to show that a dimension is less than n, we have to show that this, in that span, in the set inside the span, I can basically eliminate everything, after n elements. I can keep at most n elements in there and eliminate everything else. What can I eliminate? Well, based on this equation here, we can write a to the n as a linear combination of everything else, right? So a to the n is actually in the span of identity a squared, a to the n minus 1. Okay, but that set there was going past a to the n, right? So a to the n, yes, we can eliminate that. What about a to the n plus 1? Can we say the same thing about a to the power n plus 1? Yes?
Negative 1 to the power n will be n minus 1 or n plus 1.
To get rid of it, you multiply by it. Yeah, you're right. You need to move it to the other side still. Okay, so a to the n I can eliminate from that infinite set, but what about, let's look at a couple more, like a to the n plus 1. Well, who is a to the n plus 1? Is a to the n times a, right? A to the n, I have that equation for it, so this becomes so a to the n plus 1 is a linear combination of a through a to the n. But I want it to be a linear combination of identity through a to the n minus 1. Can I get rid of a to the n in there? I mean, not just by deleting it. Can I replace it by something? Okay, because I have it. Yeah, so I have it up there. I can just go ahead and replace a to the n by what I have above. I don't feel like writing all this again. I'll put a star. Okay, so a to the n plus 1 is in the span of what set? Well, in the star formula, we have everything from identity to a to the n minus 1, and then we have again a through a to the n minus 1, so same set. What I'm trying to convince you now is that all the powers of a greater than n will be in the span of the same set. A to the n was there, a to the n plus 1 is there. So now if I go to a to the n plus 2, I kind of repeat the same idea. I multiply everything by a and go from step to step. So in conclusion, span of the original set, the one with dot dot dot, is the same as the span of this set. And maybe you can eliminate more than this depending on the actual characteristic polynomial, but I don't have any control there. I don't know anything about it. So all I can say is that the dimension is at most the cardinality of this set, which is n. Right, because it can happen that there are more, connect relations or linear combinations in that set that we have no control of, but you cannot exceed n. And that is what we need. So as I said, I'll try to make the second question more meaningful in the sense that things might be connected to each other. It would have a nicer meaning, but the idea should be in this direction. Are there other questions, like from the homework or anything else? Yeah.
In general, so for the first problem with the eigenvector, it's going to be more of like not as much proving things, but doing.
It could be theoretical as well, but there will be the doing part as well, the computing the eigenvalues and eigenspaces, that will be there, and checking whether it's diagonalizable, and QDQ inverse will be there. Because that's an important part of this course, being able to actually do this stuff. But there might be some more, theoretical things. So in which direction, probably maybe examples that we've done in class or homework problems would be a good direction to look for that. Yeah.
Did I hear you correctly when you said homework was not going to be collected?
It's not going to be collected because I've been requested for feedback and for solutions, and there is no way to post solutions long enough before the exam so it's meaningful to you, and it just didn't make sense. So But please take the time to work on that. I will post the homework tomorrow, probably. I haven't written it yet, so.
All the suggested thoughts up there now?
Except the one with the determinant of the block matrix, because I didn't. I kept telling you that something will be assigned as homework, the determinant of A, B, 0, C as a block matrix equals determinant of A times determinant of C. Of course, I couldn't do that directly into Canvas, so I had to write those matrices in a different program and import, so I didn't do that, but it will show up on the solutions.
Could it be covered on the test?
I'm not going to ask you specifically to compute determinants on the test, so you'll have to compute them for, maybe who knows what purpose, but for eigenvalues and stuff. So determinants of chapter 3 and 4 are not going to be there. However, chapter 3 is about solving systems of linear equations, which again will show up in computing the eigenspaces. So if you have any problems with that, take a look to chapter 3.
Would you be going to do one of the questions?
Sure.
84G.
Can you tell me what page that is?
257.
So I don't have to write the solution then if we do it now, right? It takes it up. So for, which one you said, G?
Yeah.
On page 257. It says, for the given operator T, find the eigenvalues and an order basis such that the matrix of T in that basis is diagonal. So find the eigenvalues. All right, so this one is T from P sub 3 of R to P sub 3 of R. P of f of x is xf prime plus f double prime minus f of 2. Okay. So P sub 3 polynomials degree 3, right? So the basis, the standard or the basis is 1x squared x cubed. So now, so I'm working on this, okay, on finding the eigenvalues now. Let me call this gamma. So to find the eigenvalues, I need to take the matrix of T in some basis, whatever I want. I choose this gamma because it's standard, right? So determinant matrix of T in the basis gamma minus T identity is going to be 4 by 4. Right, so let's see what the matrix is. So we start with T of 1. Derivative of 1 is 0, second derivative is 0, the value of 2 is 1, so negative 1. Negative 1, 0, 0, 0. P of x. Derivative is 1, so times x is x. Second derivative is 0. The value of 2 is 2. So x minus 2, negative 2, 1, 0, 0. T of x squared. X times 2x. Second derivative is 2. The value of 2 is 4. So 2x squared minus 2. Negative 2, 0, 2, 0. And T of x cubed. X times 3x squared plus 6x minus the value of 2, which is 8. So negative 8, 6, 0, 3. Take this away from here. So now I need the determinant of gamma minus T identity 4 by 4. Okay. Fortunately, it's upper triangular, right? So the determinant is just the product of the main diagonal entries. So it has 4 eigenvalues. Three, 2, 1, and negative 1, each with multiplicity 1. Which automatically tells me that the operator is diagonalizable, right? Which didn't seem to be a question. They were telling you that it is diagonalizable, so you had to find the eigenvalues and the basis beta that makes the matrix diagonal. Clearly, that's not gamma, because in the basis gamma, the matrix is not diagonal. It's upper triangular, right? So how do we find the one that makes it diagonal? If it makes it diagonal, it's going to be a basis of eigenvectors, right? The eigenvectors will make the matrix diagonal. So in order to do that, I need to find an eigenvector for each of those 4 eigenvalues. So you have to take each eigenspace and find that element in the basis. You want to do all of them? Can I do just one or?
Starting with negative 1.
Yeah, let me start with that. Is that where you have problems? Okay, so E lambda 4, right? That's null space of A plus... Oh, that's the one you asked me before. So is the matrix the same as yours so far?
Yeah.
Okay. Okay. So I'm adding identity. 0. Like this, right? I'm not reading from the right thing, but looks good. Okay. This times x1, x2, x3, x4. Give you 0, 0, 0, 0. Negative 2x2 minus 2x3 minus 8x4 is 0. 2x2 plus 6x4 is 0. 3x3 is 0 and 4x4 is 0. So x3 is 0, x4 is 0, x2 is 0. And we don't know anything about x1. That's the problem.
Yeah.
We don't know anything about x1, so x1, because it doesn't show up into any of the equations. X1 is free, so then the solution looks like this. So E lambda 4 is the span of this one. So that would actually be the last or first, whatever. Actually, you're supposed to find the basis better. You just take this and throw it in there. It doesn't matter which one is first, which one is last. Right, so this one goes into beta. And then you do the same for each of the other 3 eigenvalues.
Thank you.
Yeah. Which one? Which is? Can you tell me the number in the book?
Pages 16.
Okay. T is a linear operator on a finite dimensional vector space V. Prove that if the characters, so part A. Prove that if the characteristic polynomial of T splits, then so does the characteristic polynomial of the restriction of T to any T invariant subspace of V. So this would be an example of a more theoretical kind of question, let's say, on the exam. It's actually a pretty good example. All right, so what is the connection between the characteristic polynomial of T and the characteristic polynomial of the restriction of T to a T invariant subspace? There is a result from last time precisely related to this in the sense that one of them divides the other. So if W is T invariant, the characteristic polynomial of T restricted to W divides the characteristic polynomial of T. Now, the characteristic polynomial of T splits over F. What does it mean that it splits? It can be completely factored out into first degree terms. So this is T minus, it's backwards, lambda 1 minus T, lambda 2 minus T, minus lambda n minus T. So now the characteristic polynomial of TW is something, I don't know what, but something that divides that product. So what can it look like? Just sum of those factors, right? Sum of those terms. So again, it is completely factored. So it splits. Just pick k of them, let's say. lambda I1 minus t, lambda I2 minus t, lambda Ik minus t. Which means that it splits. RB. If the characteristic polynomial of t splits, then any non-trivial t-invariant subspace of V contains an eigenvector of t. So it definitely has to be related to part A. So let's just say that W is the t-invariant subspace of V, non-trivial, so not the zero vector only. And according to part A, well, according to the whole thing in part A, the characteristic polynomial of T sub W but the characteristic polynomial of T sub W has to look like this, right? It's going to be a product of some of those terms, right? But the characteristic polynomial of T sub W gives you the eigenvalues of T sub W, right? So the eigenvalues of T sub W are the ones listed above. Those are all the eigenvalues of T sub W. Okay. But, so it's at least one of them, right? Has to be at least. I'm going to take the first one. What happens, well, if that's an eigenvalue, it must have an eigenvector, right? Let's call it V. Now, where should V be, the eigenvector? It is in the big space V, but let's remember that we're dealing with a restriction here. The restriction of T to W. And W is T invariant. So when I'm applying something, it should be in, I'm talking about the restriction to W. So the eigenvectors of the restriction can only be in W, right? This is a linear operator from W to W. If I'm looking for its eigenvectors, they have to be in W. There is nothing else outside W for this transformation. Okay. But what do I have to show? That this W contains, in fact, an eigenvector of T. So this V that we have here, that is in W, is an eigenvector of TW. Is it also an eigenvector of T?
Well, that's
Yes.
the eigenvalues.
And because since V is in W, T or restriction doesn't matter, right? T and T restricted to W are one and the same on this space W, right? So T is also an eigenvector of T. Actually, I take it back. I mean, this is more like playing with the words, I would say, and with the definition. So it's maybe not a good example of a theoretical question on the exam, but it looked like it at the beginning, but I don't like it anymore. It's not doing much, right? I'm just stating some definitions and a theorem, and that's it. Now, since you're all here, I wanted to ask you something. So we missed 2 lectures, right, because of the hurricane, and there is just no way I'm going to finish this material in these conditions. So I would like to schedule some makeup sessions. Now, I'm not sure how that works with your schedule, but if it doesn't work, I can do this. I can make them online, purely online, which you can attend or not if it doesn't work with your schedule, and you can watch them after. What do you think? Now, I can send you an email and let me know what would be the best available times for you, right? And if we can find something that would, I want to find something that would work for everybody, so everybody has the option to attend, online or not, you know, so. It could be during the weekend as well, it doesn't matter, because I can do this from home as well, you know.
How many sessions?
I'm thinking about 1. But right now, even with 1, we'll be stretching it, but right now, just no chance. I mean, we just finished chapter 5, and the main things of this book will be in chapters 6 and 7. So, the main ideas of the inner product space is singular values and so on. So anyways, let's not worry about this now. So first the exam on Monday, and then we'll discuss about this. Okay? Do you have other questions? All right, I'll stop here then.